students. Welcome to Nuclear Physics Lectures. In today's lecture, we will talk about uncontrolled chain reactions. The best example of which is the atomic bombs, which is also called the fission bombs. I'm Dr. Pervez Ahmed. So before to proceed toward the lectures, first of all, you should have a brief view of the uncontrolled chain reactions. And the previous lecture, we talked about the fission chain reaction. So here you can see it here how we initiate nuclear fission chain reactions or an uncontrolled fission chain reaction. So we have a target of uranium 236. We have a target uranium 235. We bombard that with the neutrons. So as a result of that bombardment, we get a complex nucleus that is an unstable nucleus of uranium-236 that go into the fissions of the two daughter nuclei, that is baryons and graptons. So as a result of that, we have three neutrons. These three neutrons, they are being accelerated for further fissions. So that means that produce further fissions. As a result of that, we get more neutrons, more fission product. So the process continues until unless we reach to a stage where the process has been uncontrolled. So this kind of reactions, uncontrolled nuclear reactions, if this is being allowed to continue, so it can be disastrous for any system or for any of the reactor in which it can be performed. That's why the best example of the uncontrolled chain reaction is that it can be utilized and the productions of the fission bomb that we also call the nuclear bombs or an atomic bomb. So before to discuss the atomic bomb or the frozen atomic bomb, first of all we need to discuss something about the fission materials. So the materials that we normally utilize inside a fission bomb or an atomic bomb, we call that enriched uraniums. Enriched uraniums, basically by enriched uranium we mean uranium 235. So what is uranium 235? Uranium 235 is basically an isotope of uranium 238, which is occurring naturally. This kind of this is the only fissile isotope found in any quantity in nature that can go and to induce fissions. I mean, when we hit it by a projectile that is a neutron, so it can go into fissions. So what is a fissile materials? Fissile material is basically the one that is capable of sustaining a chain reactions of nuclear fissions. You know that the naturally occurring uranium that we call uranium 238 uh, the naturally occurring uranium ore that we call uranium 238, it has the fissile isotope that is uranium 235 only in a small fractions, which is equal to 0.71%. I mean, this is the quantity of fissile isotope that is uranium 235 found in naturally occurring uranium ore. So naturally occurring uranium ore basically contain 99.29% of uranium 238. The rest 0.0% is being the fissile isotope of uranium 235. So what actually we do the enrichment of uranium 235 from uranium 238. So the process of enrichment, that is means the process by which we can get pure uranium 235 that we also call fissile isotope of uranium. So there are many processes for the enrichment. I mean, enrichment can be performed thermal diffusion, gaseous diffusions, gas centrifuge, ZEP centrifuge, aerodynamic process, electromagnetic isotope separations, laser process, chemical method, and plasma separations. All these are the process for the uranium's enrichments. So I mean, the fragile the materials. I mean, it can be found in different grade. The first grade we call the weapon grades. It contains almost 87% or more of uranium 235. I mean, whenever you hear the words, I mean, vapor grade uranium, so what it mean? It would mean that it contains 85% or more of uranium 235. Though for a crude and sufficient weapon, 20% is sufficient. So that we call weapon usable. I mean the weapon usable amount is only 20%. So I mean there you should differentiate between the two quantity or the two amount of uranium 235. One is 85% unfair and the other is 20% favor. I mean, if you have a quantity that is, which contain uranium 235, an amount equal to 85%, we call that weapon grade. But if it contain at sufficient amount that is only 20%, so we call that weapon usable. So uranium 235 is one of the very few atoms that can undergo induced fission. You already know about this fact, and we already know where calculations of energy from nuclear fissions. You know about this fact that the fissions of one atom of uranium 235 generate 200 mega electron volt of energy, which is equal to 3.2 into 10 raised to power minus 11 joule. So the remaining amount, that is, once we get the enriched uraniums from the uranium ore, we call that uranium depleted uranium. So what is depleted uraniums? The 238 uranium remaining after enrichment is known as depleted uranium. The other materials which can be utilized, or the other element which can be utilized as a fission material, is plutonium. It means that plutonium is another element that can be most openly utilized in fission weapon or nuclear weapons. Plutonium is the most important isotope of plutonium 239 with a half-life 24 or 110 years. So it's a key fragile component in modern nuclear weapons. Why? The reason is because it can be made from natural uranium. I mean, you know that you already know that natural uranium, that is uranium 238, contained only 0.71% of uranium 235. So we have to do the enrichment process for getting more and more uranium 235. So that is a quite tedious job. So in order to avoid that, the scientists mainly found the other alternative, that is making plutoniums from uranium 238. I mean, natural uranium, that is uranium 238, is very easy to be converted into plutonium. So that's why we're saying that plutonium can be made from natural uraniums. Mainly used due to its ease of fissioning and availability. I mean, it's easily available as compared to uranium 235, and it can easily be made from the naturally occurring uranium. The critical mass for an undepleted spread of plutonium is 16 kg. When used of a neutron depleted tamper, the pad of the plutonium and a fission bomb is reduced to 10 kg, which is a sphere with a diameter of 10 centimeters. So it means that complete detonations of plutonium will produce an explosion of 20 kilotons of TNT per kilogram. So unlike that, you can also have uranium 233. So what is uranium 233? Uranium 233 is an artificially produced isotopes of uraniums, which is being bred from thorium 232, 232 and nuclear reactors. So the fragile properties, this is one of the uranium isotopes that we can artificially produce in a nuclear reactors uh, from the thorium 232. But the fragile property of uranium 232 is not that of uranium 235. So what it mean? It means that the properties of uranium 233 varies between the uranium 235 and plutonium 239. It can occur anywhere between these two or these two isotopes. These two element are fissile materials. So let's come toward the discussion of the atomic bombs. So normally, as we discuss, we have two kind of the atomic bomb. The first we call the gun type bombs. So how it look like here, you can see it here. It's like a gun type. So just like here, you can see the red portions. Is basically have the explosive propellant, uh, and the next sections here you can see the gray part. The gray part here, we are saying that they are being directed by or pointed by the two arrow. These are basically the subcritical masses. So the two subcritical masses of uranium 235 are brought together when explosive charge, creating a sample that exceeds the critical mass. This is the basic design of the gun type atomic bomb. So what actually we have on one side, that in red color is the explosive propellant, and then we have the subcritical masses. They are being arranged on the sides. Uh, and here we have the initiator. So what actually we do, first we bring these two subcritical masses to generate a critical mass. The mass that is necessary for as a self-sustaining chain reactions. So first, what's the process? First we when we want to initiate the nuclear reaction in a bomb. So first of all, we bring these two subcritical masses together, and then from here we have initiators. From here we fire neutrons into this critical mass, and this neutron, it initiates the fission chain reactions. So the initiator introduces a burst of the neutron, causes the chain reactions to begin. So this is the sample principle, the sample construction of the G-type of atomic bomb. Uh, the example of the G-type or the gun-type atomic bomb is basically the one that we call Little Boy, and it was being utilized or being dropped by the United States of America on Hiroshima on August 6, 1945. Um, and this kind of bomb contained uranium 235 as a fissile materials, and the people who have been killed in numbers that range between 80,000 to 140,000. These number of people that have been instantly killed with the explosions of the little boy. The second type of the bomb that we call plutonium implosion is basically implosion-type bomb, and like you can see it here, in this kind of bomb and this kind of the devices, we basically have the plutonium inside the core, and the explosive they are being poured outside the core. So what actually we have, the explosive charges compress spare. Whenever we want to detonate the weapon, so what actually we need to do, the explosive which are here, you can see it here, like in the this big circle around this hollow plutonium core. So what actually we do, explosive charge, these are the explosives. The explosive charge compresses the sphere of the plutonium quickly to a density sufficient to exceed the critical mass. So the example, of the explosive or the implosion type bomb is the Batman, or we can say that the example of the plutonium based implosion-type bomb is the Batman, and it was the one which been dropped on Nagasaki by the United States of America on 9 August 1945. So the number of people who were being killed during the explosion of plutonium implosion-type bomb is range between 74 to 75,000. I mean, the major estimate indicate that around 74,000 people and roughly the same amounts being injured during the explosion of Pitman. I mean, the bomb that's been dropped on Nagasaki by the United States. This all we have for the uncontrolled chain reactions or for atomic bomb. So this all for this lecture. See you in the next lecture with further detail of nuclear fission. Till then, bye bye.